So a few weeks ago, from when I'm making this video, one story kind of went viral. It was a story about this coming from China. The first commercial supercritical carbon dioxide power generator that was apparently turned on in China on December 30th, 2025. And this generated quite a lot of buzz in the news and quite a lot of excitement, but I think most people, including people that I know, could not actually figure out why, or specifically what exactly was achieved in this case, and why is this kind of important and kind of interesting. And so in this video I wanted to actually focus on this idea of supercritical carbon dioxide reactors and why in theory they actually have a chance to dramatically improve technology on the planet, and specifically improve energy generation and thus reduce the amount of emissions, despite the fact that this is all based on carbon dioxide. And so, hello wonderful person, this is Anton. Today, let's discuss this phenomenon and why it's kind of exciting, but also discuss this achievement from China that's referred to as CO2-1. Although as always, this is also going to be based on several studies, and specifically studies examining exactly how this phenomenon works and how efficient it is and what we can possibly use it for in the future. But I guess let's start with the basics, because in this particular case it's a little bit easy to misunderstand what's actually being achieved. And while historically, for over a century now, the entire modern world has been mostly powered by the same technology, the steam technology. And we're not just talking about steam trains and steam engines, we're actually talking about everything around us. For example, coal plants, nuclear power plants, natural gas facilities, and most engines usually use the same basic physical principle. They usually use a turbine that's actually moved because of steam generated by boiling water. And so even though it all started with something like this, today a lot of these devices use a very similar Rankine cycle, as it's also known, that basically involves a pump, a boiler, and a turbine. But the problem here is actually the fact that we have to boil water. And turns out that by boiling water, we're wasting a lot of energy. Basically, boiling water is extremely energy inefficient, making this type of an engine basically waste a lot of energy on turning liquid water into steam. But nevertheless, for over 100 years, this is what we basically used. But the question is, what if you don't use water, but use something else? And so today we're going to discuss a massive shift in energy production, or basically an idea that moved from just being a theory and a lab experiment into the real world. We're going to discuss supercritical carbon dioxide. And while to understand what this is, let's take a look at this video from the SUKU lab in University of Dresden. Here this is going to show us a phase transition that carbon dioxide goes through as you increase temperature and as you increase pressure. And so in essence what you're about to see is a transition of the carbon dioxide from a liquid into what's known as a supercritical carbon dioxide. Something that happens above 31 degrees Celsius or 87.7 Fahrenheit, and at pressures of approximately 7.37 megapascals. And it kind of starts to look like this. This is the supercritical state. And in this state, CO2 becomes a bit of a hybrid. It's not a liquid, it's not a gas, it's something in between. It basically expands to fill the container just like a gas, which basically means it has very low friction, but it also maintains the density of a liquid, which is of course not a state of matter we're used to. Normally for CO2, we're sort of used to it being just gas as we exhale it from our lungs, or sometimes we get to see it as dry ice when we buy something from a grocery store. Yet this study and this entire research is basically based on this state, the liquid-gas hybrid, because apparently this is very useful for a lot of different things, but especially for moving energy. And here you can think of it this way: because it's dense like a liquid, it can actually push the turbine with a lot of force, but without losing too much energy to friction, because it can also flow like a gas. And so here it can easily move through pipes without losing energy like water, which makes this incredibly important for the efficiency of the system. And that's because the traditional steam engine usually has a lot of little parts inside that usually force it to lose way too much energy. But once again, it's really that phase change that requires the most amount of heat. And that's not something supercritical CO2 needs to go through. And while based on a lot of previous research, scientists discovered that if we were to replace water with CO2, in theory it can reach efficiencies of 50% or higher. And that's compared to approximately 38 to 40% for a typical water-based engine. But the reason you're hearing about this now is because finally, There's actually been some major breakthroughs in just the last few years, and especially some major engineering bottlenecks. And that's because for many years, engineers struggled with one major problem: how this supercritical CO2 affects the materials. And that's because at high temperatures and at high pressures, it can also be quite corrosive. But recent studies discovered that some materials are not actually affected by it, and especially nickel-based superalloys. On top of this, they also redesigned the overall structure of the engine and developed what's known as printed circuit heat exchangers, highly compact microchannel heat exchangers able to handle massive amounts of heat in a very small space. And so in just the last 10 years, quite a few different teams from across the planet created a lot of theoretical concepts and even prototypes that actually worked. And the best part about all of this was actually size. Because the fluid here is so dense, and because a lot of the parts are so small, the actual turbines can be tiny, with some of the earlier designs suggesting something that was very small, something that you can actually keep on your desk. And so in most cases they would be at least 10 times smaller than a typical steam-based engine. And that's despite the fact that it produces the exactly same amount of power. And the first such proposition was back in 2014-2013, when some of the engineers from MIT created their first sample. And while here they also discovered something else incredible about this design: operational flexibility. For a typical steam-based engine, it usually takes at least 30 minutes to warm up and start generating power. That's mostly because water has to become steam first. But for a supercritical CO2 system, this can all be done in just 2 minutes, which actually makes it perfect for a modern grid that usually depends on a much faster response, especially because of a lot of renewable energies that can usually switch on and switch off much quicker. And so integrating this type of a system into a modern grid provides way more benefits. And while for the past 2 decades or so, the United States has mostly been the leader in this technology, there have been some European teams as well, but they haven't gotten as far as the US. And while one of them is based on some of the early research from Sandia National Laboratory, that essentially created their prototype you see right here. Here they created a prototype that was able to generate electricity that even a few years back was able to produce approximately 10 kilowatts. But more importantly, this was an official proof that all of this seems to function well, and it's able to integrate with the commercial power grid without disturbing it. And so this was actually a really important proof of concept. But then just over a year ago, in May 2024, a much larger project referred to as STEP Demo, with a facility in San Antonio, Texas, was able to successfully generate 4 megawatts, reintroducing it into the grid. And so this $150 million project that was designed to prove that this technology works was finally able to show that it does work and can even function for a long term in relatively hot conditions of almost 720 Celsius. And so in 2024, this was actually a pretty big achievement. But the thing is, these US projects were actually mainly focused on something slightly different. They were trying to prove that these designs are relatively secure and relatively safe. And that's because the main use for them would be in nuclear technology in order to replace water-based nuclear reactors with something that's a little bit more efficient using supercritical CO2. And so they were not really inventing a new steam engine as much as they were trying to improve nuclear power plants. And so for a year and a half, we pretty much heard nothing. And that's until China said, "Hold my beer." In this case, I guess it's Tsingtao beer. And out of nowhere, we had this Chinese announcement that kind of blew everyone away. And that's because here they created something that's completely different in terms of scale and in terms of development. On December 30th of 2025, China announced Chaotan 1, the world's first commercial critical CO2 power generator. And so while US was focusing on research and pilot plants, here we had something that was already working and something that was already commercialized. And that's actually what makes this different. Now, first of all, the capacity here was very different. Unlike the US plant that was able to produce 4 megawatts, here this plant that consists of 2 units is able to produce 30 megawatts, which is nearly 10 times as high. On top of this, unlike the pilot projects in the US, this was a commercial project. This is not a lab experiment, it's already connected to an existing steel plant and is able to recover waste heat from that steel plant in order to then produce energy, with the energy supplied to the main grid. And so basically here, this is all based on waste heat coming from a steel plant. The plant produces a lot of extra heat, the heat is then being captured by the supercritical CO2 engine, and the engine produces electricity. And right now, all of the reports suggest that the system is at least 85% more efficient than any of the older systems this factory was using. And it also provides 50% increase in net electricity output. But once again, what's even more impressive is that it's even smaller. Right now it takes up about 50% less space than before. Or I guess just to make this fair, here the comparison is to the legacy systems that were used in this plant, and not to some of the most modern and most advanced steam engines that might be a little bit more efficient. But even with that context, the fact that it's connected to the grid and is already generating revenue marks this as a major achievement, a major global transition in technology. We no longer have to use water, we can now use supercritical CO2. And well, studies like this coming out of China essentially tell us what's basically the next step. Here, this particular study is basically based on a very similar design and presents a lot of exciting discoveries that can redesign a traditional nuclear power plant, which will then rely on supercritical CO2 for generating power. And so here, once again, instead of using steam and losing a lot of efficiency, the point is to use supercritical CO2. And this is basically the main goal for a lot of different teams. Because by redesigning nuclear power plants and by creating something that's at least 20 to 30% more efficient, it will suddenly allow us to create so much more energy by basically using the same amount of nuclear material. And more importantly, it will make them simpler and safer. Because this uses supercritical CO2 as a direct coolant, it actually eliminates the need for steam generators and a lot of primary pumps and pressurizers. It basically makes the nuclear plant much less likely to fail and much less likely to have problems. And that's because in a traditional power reactor, losing these pumps can be a disaster. But for these types of plants, if the gas cooling is ever lost, the heat will simply radiate into surrounding heavy water, preventing any potential meltdowns or any potential disasters. And so once again, by using supercritical CO2, a lot of these nuclear reactors can be much smaller, much safer, and even much cheaper to build because they require a lot less systems. And well, right now looks like China is sort of winning the race. Now the American power plant is obviously still works too, but unfortunately it has not been commercialized yet, and it's still just a proof of concept. And so for the future of technology, these are definitely some really exciting discoveries. But they're also exciting because they're just going to make things so much more efficient. For example, for a typical steel plant, it will actually recover approximately 7 to 8% of global greenhouse emissions, while also producing extra electricity, making the plant much less wasteful. On top of this, it also allows us to suddenly build a lot of these power plants in locations where it was previously impossible. And that's because before, we usually build these plants close to water sources. But for a supercritical CO2 system, since they're so compact and so efficient, they could actually be built pretty much anywhere, even in remote locations in the desert, which is actually what China is planning next. Their plan is to basically build a bunch of these in the middle of Gobi Desert. But whether they succeed or not, only time will tell. Either way though, 2025 was officially the dawn of new power systems. Or basically we officially saw the introduction of completely new steam engines that have now moved from being prototypes and being theory to an actual 30 megawatt power plant that's now producing commercial energy in China. Although here there might still be some challenges. Because this has just begun, we have no idea if there are going to be any long-term problems. And especially because once again, critical CO2 under very high pressures is actually incredibly corrosive. And so we don't really know if it's going to cause any problems for this power plant after several years. But once again, only time will tell what's going to happen here, and for all we know, we might have just entered a completely new era of energy production. But that's, I guess, of course, assuming everyone else can catch up to China and start making something similar in their own country. And so I guess the question is, did we just finally reach the end of the steam age? Have we just entered the age of supercritical CO2? Well, let me know what you think about this in the comments, and once we have some updates, we'll come back and discuss this more in some of the future videos. Until then, thank you for watching, subscribe, come back tomorrow to learn something else, support this channel on Patreon where you can find additional videos without any ads and can DM me directly, or by joining a channel membership that grants you early access. You can also support this channel by buying the Wonderful Person t-shirt in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye bye.